Okay. Hi everyone. How are you doing? How was last week? Ah, intermediate, easy.
Any advice for translating? Because it's easier to just kind of write them on paper, but it's just so hard to follow what you're doing when you're just writing in your text.
Yes, it takes time, but after that you can do it easily. In the second semester it will be more easy. Yes, more of that. So today we in week 3, recitation number 2. Okay, here you can see, you can find our materials. I put it here. Yes, if you don't know this. Okay. So this is our course. This is our course, Probability English Master. It's the first one. Today we in the recitation number 2, as you see. And here all the materials, slides, quiz, homework 2, homework solution, not ready yet, and mind. Okay, so now I'm entered to these 12 slides and we will start. Hmm? Yeah, no, it's Canva. It's for schools. It's Canva. It's very easy. Okay. So this is our slides for today. This station slides number 3 and 4. It has 2 parts. Part number 3 and part number 4. We will start from the second part about conditional probability. And if we will have enough time, we will also talk about part number 3. Okay. 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 Conditional probability, independence, formula of total probability, Bayes formula is a very important tools from the probability. I assume you know these tools from the previous courses, but it's very important to review and to solve questions according to this material. So, formula of conditional probability is very, very useful. We can calculate probability of some event given additional information. And the probability of event A given B, by definition, equals to probability of A B divided the probability of B, given that probability of G is greater than C. This formula is very, very important. Why? Because in our life, most of the equation is a question of conditional probability. What is the probability that a student will success in our course given he solves every problem? It's high or not high? What do you think? It's supposed to be high. Yes, it's supposed to be high. What is the probability that the student will success in our course? In the day before, he drinks a lot of beer. It depends. Yes, but probably it's low. We don't know. Oh. So this question, this conditional probability is very, very important. Oh. Second rule, multiplication rule, has another name, chain rule. You see, it's kind of it's also very important rule. Not only probability of statistics, also even stochastic processes and other fields. It gives us the way to find the probability of intersection of many events. We can solve this gradually. First of all, we find probability on A1 times probability of A2 given A1 and A2. Times probability of A3 given A1 and A2. And we continue in such way, and we find very useful tool. We will see today an example how we can use. Okay. The formula of total probability. It's very, very important. I want to explain it here, and we will demonstrate how we can use it. Okay. When and how we can use formula of probability? Suppose we have some sample space and we have some complex event. This is complex event. It's not fish or something, it's complex event. And suppose our goal is to find probability of A. Why? Because it's important for us. But we don't know how. Because it's a complex event. We don't know. We don't have any idea how to find probability. In some cases, not always, but in many cases, the formula of total probability can help us. How? The idea is divide and conquer. If you for computer science, you know mathematics, probably know it. The idea is to divide with omega to sub-region. For example, region number 1, region number 2, region area 1, 2. Okay. This is partition of omega. And now the probability of A equals the probability of A in this part, intersection H part, yes, plus probability of A in this part, intersection H2, plus probability of A intersection H2. This is the formula of total probability, that's all. This is the idea, yes. And in many cases, it can be very, very useful, we'll see it today, to find probability of A in this way. Divide to smaller part and conquer and solve. This is idea, yes? This is the same thing. But now here we have many questions. First question for you. Suppose we have some omega sample space for any question, it doesn't matter. And we want to divide it to build partition. How many partitions exist in general? 1, 2, infinitely many. It depends on the omega, but there are many partitions. In some cases, it can be infinitely many partitions. So the question is, how we can choose the partition to solve the question? Yes, our goal is to find probability of A. And to find probability of A, we need to find partition and find probability of A by using the formula of total probability. And the goal is to find good partition. It's easy question or no? Or depends? It depends. It depends on question. Sometimes it's what you say. Sometimes it can be something else. Sometimes it can be very, very good. Okay, depends. There are infinitely many partitions of the same omega. You can divide it in this way. We can divide it in such fuzzy way. Yes, there are infinitely many general partitions of omega. Some of partitions, we'll see it today, now, in 5 minutes, will help us to solve the equation, to find probability of A. And some partitions won't help. So your intuition, your solution of combo will help you to build your intuition, but it's not easy. It can be very, very, very hard to find a good intuition. But if you're lucky and you find it, you can use the formula of total probability and solve the equation. Okay? The idea is clear. We will demonstrate it in a couple of minutes. And the last fellow, also very, very important. It's a formula of Bayes formula of C Bayes. Also very, very useful. And its idea is very simple. Suppose we want to find probability of A given B, the conditional probability, and in many cases, it's convenient to find it using the Bayes formula, Bayes rule. It's probability of B given A times probability of A divided by probability. That's a famous Bayes formula. That's all. When we can use it and why we want to use it. What is intuition to use this formula? What do you think? If you know how to find this probability, you don't need Bayes formula. You find it, yes, that's all. But if you don't know how to find this probability, but you know how to find this guy, and this guy, you can use Bayes formulas. If this fellow is easier to find than this fellow, yes, probably you need to use Bayes law. This is it. Okay, so this is a material, and now we will solve a couple of interesting questions. Before we start, any questions?
Unless I can find this. Look,
It's you find slides?
I found if you go on the thing, you see probability recitation. That's the recitation 1, 2, 3, 4, right?
Yes, yeah.
Yeah.
Recitation 2,
Click on recitation 2,
slides.
and I click on slides, and it just takes me to a different.
No, it has too many slides. Okay, just a moment. Recitation 2, slides. You must be here.
Yes, I just don't
And you need to go down. Yeah, just a moment. Yeah. 1, 2, 3, 4. There are many. See? There are many questions. Probably 9. And that's all. Recitation 4. Okay. Any questions about review? It's clear? Okay, let's start with a couple of questions. Anyone plays chess? Likes chess? Watch film about chess? I think. Okay. It's not so popular today, probably, but we can solve here some interesting questions. Anyway, so it's a good example how to use probability law. Okay. So what we have here? We have chessboard, regular chessboard. Let me draw it. 8 by 8. This is regular chessboard. Has 1, 2, 3, 4, 5, 6, 7, 8. We need 68 squares. Okay, we take two bishops, two tools from chess, and place them randomly on the chessboard in some two squares. For example, we put V1 here, and the second one. These are two bishops. Okay. And the question is, what is the probability P? What is probability that they will attack each other? The question is how we can attack, yes? How we can attack? How bishops attack? By diagonal. Yeah. Bishops can move and attack by diagonal. These and this fellow can attack here, here, here.
It's probably that they're able to attack. Like,
If this bishop attack every
is able
diagonal,
to attack.
every.
Yes.
Okay, so this is the question. It's probability question, yes? Yes. You have a chessboard, see 8 by 8, 8 rows, 8 columns, and you put here randomly, yes, two bishops. You can't put them on the same place, yes? You can put them one here and one here, one here, one here. You can put them on any two squares random. And the question is, what is the probability that these two guys will attack each other? When they attack each other, if they stay on the same diagonal. For example, yes. If the first one stays here and the second stays here, they stay on the same diagonal, yes? So they attack each other. No, in this case. Yes, but it's must happen, yes. But if the first one stays here and the second one stays here, they don't attack each other because they don't stay on the same diagonal. And you want to find probability that they will attack each other. It's not one. It's not something between 0 and 1. Yes, depends. We need to find this. Okay. For example, okay, look on this example. If we have small chessboard, 2 by 2, You put first one whatever you want, doesn't matter. And what is probability we will attack each other? The probability is 1/3, yes? Because if you put the second one here, we will attack each other, and if you put it here or here, it's will not. So for this board, which answer is 1/3. But it's clear because it's very, very small board. And we want to buy solution for large board, 8 by O and J, N by S. Two pieces. You have two pieces, you put them randomly on the chessboard. And what is the probability that they will stay on same diagonal? So this is
So we put first one somewhere.
Yeah.
Then you have two base, row and column. Like
oh, it depends. What depends? Let's see. Oh, your starting point is clear. Okay, so we have two bishops, two tools, and to put them randomly, and we need to find probability that each we attack each other. Excellent. Now let's try to understand this question. Suppose first bishop will stay here. For example, yes, it's only example. In the corner. In this case, how many squares he will attack? 7. I can find 1, no, 2, 3, 4, 5, 6, 7. If the first bishop stays here, he will attack only 7 points, only 7 squares. Make sense?
Yeah.
Okay, you can check this square or this or this or this or this. Any of these points, any one of these squares, if we put the first bishop here, it will attack 7 points. But if we put the first bishop here, how many squares it will attack? We can count. Yes, 1,
also 7 now.
no, 2, 3,
Ah,
4, 5, 6, 7, 8, 9. If we put the first bishop here, it will attack 9 squares. Yes?
Yeah.
If we will put it here, 1, 2, 3, 4, 5. Where we put it? I want here. 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Also 9. So if you put first bishop in one of these squares, in one of these green squares, it will attack 9 squares. If you put the first bishop in one of these, it will attack 7. Oh, so this will our partition, not this. This will our partition. 1. Oh. Let's continue. If the first bishop in this square, for example, here, how many squares it will attack? We need to count, yes? 1, 2, 3, 4, 5, 6, 7 on this diagonal. 8, 9, 10, 11. So for every point here, yeah, on this square, the first bishop will attack 11. And this last guy, for any bishop in this square, or this square, or this square, or this square, you can guess how many squares it will attack. So third, yes, 7, 9, 11. Well, what you can choose. Okay, so we try to understand the equation, and we see what we learn, that the numbers of the square the first bishop will attack depends on this position, of its position. Yes? And we see that there are 4 types of positions. Yes? Okay, this gives us partition. This gives us 4 partition to 4 sub areas. H1, H2, H3, and H4. Yes, 1, 2, 3. And now we can use gradually slowly, a formula of total probability. So let's try to use it together. Okay, P, probability that we attack each answer. Let's denote it by P. It equals by the formula of total probability, P of A, given the first bishop stays on this, on one of these points, H1. Times probability of H1. We need to find it. Plus probability of A, given the first bishop stays on some of these squares, H2. This is H2. Times probability A given H. Plus probability of A given H3. Probability of H3. Plus probability of A given H4. Times probability of H2. This is our partition. And we hope it will help us to solve the question. Does this be only one possible partition for this question? No, there are many partitions. For example, you can divide, you can make here partition for 64 elements, yes? Every square is partitioned, H1, H2, H3, H5, until H64. You can, but it's very long solution. There are not indeed, there are many partitions here. But this one is good. Why? Because it will give us simpler solution. There is a probability that two bishops attack each other. This is what we want to find. Speed. A is a when two bishops attack each other. What we want to find? We want to find probability of A. And we find probability of A using the formula of total probability. And now we need to find every one of these terms. Let's start from the first term. Look on this page, yes. We know that the first bishop stays, for example, here. This is H1, yes? What is the probability that he will attack the second bishop? You need to calculate. The first bishop is here. You put second bishop whatever you want, except this point. What is the probability that first bishop will attack the second one? You need to calculate how many points he attacks. How many points he will attack if he stays here? 7. How many points are empty? 63. Yes, so probability of H given H1 is 7 divided by 63. There are 63 points for second bishop. And the first bishop only attacked with 7 points. So it's 7 divided by 63. What is the probability of H1? What is the probability that first bishop will stay on one of these squares? Yes, we need to find how many squares we have here. One, two, we need to calculate. Divided by 64. Okay, 8 plus 8, 16, plus 6, 22, plus 6, 28. Yes, 28. So the probability of H1 is 28 divided by 64. This is the first step. Now the second one. We know that the first bishop stays on some of these points. Okay, for example, this point. First bishop is here. What is the probability that he will attack the second bishop? 9. It's 9 divided by 63. Again, it's 9. It attacks 9 points, 9 squares, divided by 63. What is the probability? Okay, I need to repeat. What is the probability that first bishop will stay here? One of these green points. We need to find how many green points we have. Yes? 1, 2, 3, 4, 5, 6. 6, 4, 4. 20 from 64. Yes. You also can see here the rule. Yes, here we have 10, 7, 9, the next one will 11, but we need to check. Yes, we need to check. Here we can 24, 28, 20, the next one will 12, but we need to check. Oh. So the next class probability of A given H3. If the first bishop stays here, he will attack, you can find 7 plus 6. 1, 2, 7 plus 4, 11 points from 63. And what is the probability that the first bishop will stay on one of these points? 1, 2, 3, 4, 4, 12. 12 from 60. Okay, and the last term. Now, what is the probability that bishops will attack each other if the first bishop stays on one of these points? If he stay on one of these points, he will attack 13 squares from 62. And the probability that the first bishop will stay here or here or here or here is 4 divided by 62. And this is the final answer. What do you say? Easy up with the media. Not easy. Yes, it's not.
I thought it wasn't so.
What do you?
I said it wasn't so bad. I think so.
Yes, it's not easy. It's not easy. I agree. It's not easy. Take that. Yes, yes, yes. But it's a good example how we can use the formula of total probability to solve such kind of questions. And the idea is to divide the complex question to sub simple question. Yes, conquer, divide, and conquer. But it's not easy. Yes, it's not obvious. It's not obvious. But let's say if somebody will give us $1 million to solve this question, we will see it, and solve it. And we will, yes, we will. Why not? Some question we can't solve for $1 million, yes, but this one we can. Okay, so here you can see in solution. See. No. You can. This is the point.
Sometimes when I press space, I wonder if what it's saying.
What do you say?
When I press space, won't preview the answer really.
Here?
Yeah, this time.
Ah, yes. Now we will use bias. Yes. Okay. So this is final answer. And as you can see, we can guess it. Yes, we need to solve this question because it's not something easy to guess. But finally, after we use it, it's 526. But it's not obvious. We can't guess it. At least I can't guess these answers. Cloud solution. Okay. Good. Can we continue? Okay, second part of this same question. Again, conditional probability. Given the previous problem, find the probability that first bishop is on A1. A1 is this point. Given bishops attack bishop. First of all, it's question about conditional probability, yes, because we can read it here, even some information. How we can solve? There are many ways to try to solve it. So, sometimes, if somebody asks you about probability of A given B, you can say, it's immediate. The answer is, do you have the answer for this question immediately? Do you see the answer? No. Without any calculation. No, I all. Yes. Sometimes it's possible, yes. For example, what is the probability that we get on a die 1 if we know that we get even number? It's 0. We don't need to start calculation. When you look, we see it. Yes.
Well, if the first bishop is on A1, the only way the second bishop, but it has to be on.
But it's not on A1. This is the question.
So it's the probability that
you need to change direction, yes. You need to use Bayes Theorem. So if somebody asks you about conditional probability in general, sometimes you can answer without any calculation, but it's rare. But it can. Okay. But it's not the case. Yes, we can't see here with us. Yes. Okay. How you can try to solve this? You can try to use definition. It equals the probability of A intersection B divided by the angle. You can try, but in some cases it's easier to find probability of intersection. But in many cases it's not too easy to find probability of intersection. It depends. Oh, but you can try this approach. Try to find conditional probability by definition. Okay, this is the second. You can try it here. It's possible. And the third way to try to solve this question is to use Bayes formula. For example, this is B and this is A. It's our notion. So by Bayes rule, it equals the probability of A given B times probability B divided by probability of A. And the question is, will this formula help us? We need to check. Yes, we don't know in general. We need to check. If we know how to find this value, and this guy, we have a solution. Oh, let's see. Let's start from this value. What is the probability that first bishop will stay in this corner? 1 divided by 40 by 64. Yes, probability of B is very easy to find. It equals 1 divided by 64. We have only one corner from 64 points. What is the probability of A? You ask me what is A. Probability that two bishops attack each other.
Just calculate.
We calculated in the previous. Yes, we found it previous. I don't remember. It was 5 divided by 36.
5 must be
By 1,030.
Something. Okay, we found. Oh. And now we only need to find this value. Yes.
This is Bayes rule.
Yes, this is very. The probability that bishops will attack each other, if we know, it's given that first bishop stays here. It's 7 divided by 63. We found it. Yes, it's 7 divided by 63. That's all. So in this question, we use Bayes formula and we found the solution. And in general, you can try use definition. Sometimes it's easier, sometimes, but to use definition, you need to find probability of intersection. But here we Bayes formula is a simple one to use. Yes.
So like yeah, we have the Bayes formula just a little bit above in recitation, but it looks like a little it's different.
You're saying probability of A given B equals probability of B given A divided probability of A divided by probability of B. And this value you can find by formula of total probability. See on some. But in general, we don't need it here because we found this previous. But this is Bayes formula. Yeah, but for in notes, instead of PUP, we use formula of total probability. Make sense?
Okay, so the bottom of Bayes formula is really just a log total probability.
Yes, formula of total probability.
And since it's only one or about the
It's formula of total probability, and we did it in the previous part. Okay.
It was very easy to calculate this because of the.
Previous chapter, yes. Yeah.
So if it's the next exercises, then we have to think about Bayes.
Yes. Okay. When you need to also need additional keys, when and why you need to think about Bayes. Pay attention in this question. The order of things is not logical. Because in the question, first we put the first bishop, after we put the second bishop on the board, and after that we check if they attack each other. Yes? And in this question, the order is changed. Where it says that we know when two bishops attack each other, it's given. And the question is, what is the probability that the third bishop only? If your order is not logical, this is a hint to try to use Bayes formula. In many cases, it will work. In many cases, it will. Makes sense? It's a good question. Yes, it's not the easiest question, but it's good itself. Okay. Okay, I want to solve now problem number 3 about cards. I don't know how many people today plays cards. Yes, as a chess. Anybody plays cards? Poker. Casino, poker. Yes, okay. So I think you need to, I don't know, probably you need to make safe S, but you need to check, yes? Oh no, you need to print, not send. Yeah, print, but you need to try. It's not working? Okay. Let's see. It seems good. Only one page? Okay, I need to ask AI. I will ask AI. Okay. You want to print it? And you don't want. Okay, I'll check it. Okay, I'll check. Thank you.
If you had one more vision, how complex is very good?
Sorry?
You had another vision.
Another?
In this question.
Yes.
How complex is very good?
If I dig the third one, it will be two-dimensional. Now it will depend of the place of the first bishop and the second bishop.
It will be a vector.
It's a vector or two-dimensional case, yes. Now we have one-dimensional partition, and in your question we have some kind of, in some case, two-dimensional partition. Okay, for computer it's not very hard because you can find right algorithm to solve this question. But for the person, get the solver sum. Okay, we'll see how you can print this or open it on tablet. I will. Okay. Question number 3. Also interesting question. It's not the simple question, but after you understand solution, it's simple. I want to demonstrate you 2 solutions to this question. One easier but tricky, and the second is not tricky but hard. Okay, so let's read this question. We have deck of 52 playing cards. Okay, everyone knows, yes, cards. We have 4 kinds, and of every kind we have 13 cards. Spades, hearts, diamonds, yes. Okay, so what we do with the cards, we randomly divide it in 5 piles for 4 piles for 4 people. Each one get 13 cards. And we want to find the probability that each pile, will get exactly 1 ace. There are 4 aces in the deck. Okay, so we have 4 aces between 52 cards. We divide randomly our cards for 4 people, and the probability is that what is the probability that each one will get exactly 1 ace. We can solve this question in many ways, and now I want to demonstrate you the chain rule of multiplication. Chain of multiplication. It says the probability of intersection, for example, A1, A2, A3, and A4. I need to define this form. Equals to probability, equal probability of A1 times probability A2 given A1 times probability A3 given A1 and A2. And the last rule times probability A4 Given A1 and A2 and A3. This is multiplication rule, chain rule from the lecture notes. We will use it now. We are going to use it now. Again, what is idea of this formula? In general, not related to this question. Idea is we want to find probability of intersection of many terms. And in general, it can be hard. But find probability of intersection can be very hard because it's not easy. And instead of calculating probability of intersection of many terms, we solve it, we find this probability by steps. First step, we assume only A1. We find probability of A1. And our hope is that it's easy to find. Okay, we find probability A1. And now in next term, we assume that A1 is given and find probability of A2. And again, we hope that it's easy to find. Okay, we find this fellow and the next step. Now we assume that A1 and A2 happen and we find probability of A3. And we continue this way. If we can find easily each one of these terms, we can find probability of intersection. This is the idea of chain rule. And now I want to show you how we can use chain rule to solve this question. And you will see, we will get very short, very easily. It's not easy because we need to understand the ideas, yes, but the solution will be very, very short. Okay, so let's. It's very good question. Okay, so let's start. Okay, we need definition. So our goal is to find probability that each file has one X. Each person will get one X. Okay. Let's denote 4 events. E1, E2, E3, and E. What is E1? Let's try to understand. This is the case of solution. Let's denote by E1 event that ace of spades is in any pile. Somebody will get ace of spades. What is the probability of E1? It's 1. Oh, that's means. But why we need it? Yes, what does it say? It said say that. So a probability of E1 is 1. It's not so interesting. Now let's define E2 that the second ace doesn't, for example, count a diamond, start. Oh. With the high ace of hearts will be not in the same person where the ace of spades. So what is the probability that ace of hearts will in other pile when ace of spades, given that ace of spades in our one? Yes. E1 is the probability that ace of spades in some E2 is a probability that ace of spades is not in a pair one of the previous ace of ace of spades. So A2 is not probability, is an event. Is an event. Is an event. No. So E2 says that ace of cards and ace of spades are in different piles in a different persons. That's all. Not with A3 set. A3 is event. We continue the same event. Z ace of hearts is not in the same pile. Where is ace of spades and F of two previous? Just a moment, what we have here? Spades has diamonds. Yes. Of diamonds. It's not. Yes. And that is for no. Okay. And if there is a event with the ace of diamonds, it's not in the same files, whereas two previous aces. And what says A4? In the last one, is a event with ace of what we have? This clubs. Oh, clubs. Is not in the same pile where is three previous aces placed. Okay. This is this four events. First, ace of spades in some pile, it's one. Probability of one is one. E2 says the probability of heart is not in the same pile where is the probability of spades. We need to find this time. E3 says it's event with the ace of diamonds is not in the same pile where is these two elements. And E4 says that the ace of club is not the same pile where is this and this things. So, yes, so these four events.
Some kind of events.
Yes, they depend. They depend. You're right. Okay. Now, what I want to find? I want to find probability that each file has one ace. Yes, that each person will get one. The catch of this question is the probability that each file has one ace, that denoted by A, is intersection of E1, E2, E3, and E4. It's the same event. Yes, it's the same. This is the catch of this. Yes. Okay. Because okay, what you suggest will give a solution, but it will harder than this one. This solution is very simple. Okay, but you don't know in the beginning that it's very simple. You need to see. But in general, we use these notions because finally we will see that it will give us very short and very simple solution. And your idea is good. You need to try it, and you will see it will give you solution, but not very short. But you don't know it from the beginning. Yeah. So I will use here this definition, not because we're very intuitive. We are not very intuitive. But finally, this definition will give us very short solution. You will see it now. So the catch of this solution is that the probability that each person will get one ace equals the probability of intersection of these things. And this equals to the probability of E1 by chain rule of probability of E2 even E1, probability of E3 even E1 and E2, and probability of E4 even E1, E2, E3. That's all. And now I state that each one of these probabilities is very simple. Okay, it's not very simple. You need to think about it, but finally it's very simple. Let's try to think about it together. What is the probability that first ace of spades, will be in some pile, in any, it's one, yes, it's one. Let me draw a pile. These 12 cards for the first person, these 12 cards for second person, this is third person, this is last. Thank you. This is 5, yes. First part, 2 part. So this is this one, yes, makes sense? Let's find this probability. We know that ace of spades in some piles, yes? For example, suppose it's here. Yes, how am I going to draw it? I don't know. This spades doesn't matter. What is the probability that the ace of hearts will be no here? It can be here, this, or here. What is the probability of E2 given A1? We need to find. The second ace must be here, or here, or here, but not in the same 5. What is probability? How many? It's not 20, it's 30, yes. 14. Okay, 5. Okay, what is the probability that the second ace will be not here? Wait, or here, or here, or here. Yes, how many possible places? 13, 13, 13. Yes, 49. But how many places we have for second eyes? 13, 13, 13, 12. From 50 to 51. Yes. So this is this term. The one place is busy. Yes, yes. What is the probability that the first ace will not? Okay, for example, let's suppose the heart is here. What is it? Right. What is the probability that the ace of diamonds, yes, will not be here and here? 26 times 50, yes. For example, and the last term is the probability that the last ace will be here. It's equals. Yes. Okay. And this is the final solution. And before we stop, just a moment. Yes. This? Okay. This is combinatorial solution. If you want to use chain rule, it's a shorter solution, yes? You can use combinatorial solution. You can choose ace and cards. It goes with this ace. And you continue this way, you will get the same solution, same answer, but as you can see, it's a long gauge, not so nice. Okay. We will stop here. I published today second combo. Okay, so if you have any questions, send me emails or ask. Okay, thank you very much. What is here? Let's stop. Yes, take a break. Yes. Some